This conference will now be recorded.
Hello students, we are
This conference will now be recorded.
hello students, welcome to the PYQ discussions on JEE Main paper 6th September morning session 2020 paper. So we have an aim to discuss PYQs of all the even years first, then the odd years we will go for. Okay, so that's why I have just cast up this.
This conference will now be recorded.
Hello students, welcome to the PYQ discussions of PYQs on JEE Main.
This conference will now be recorded.
Hello students,
This conference will now be recorded.
hello students, welcome to the PYQ discussions. So we have been discussing previous year's questions from JEE Mains paper. So today we have picked up few problems from JEE Main 2020 6th September paper, and this is I think SIP morning. The course this paper is from 6th September morning or shift 1. Shift 1. So let us start our discussions. The first question says a clock has a continuously moving second hand of 0.1 meter length. Average acceleration of the tip of the hand in units of meter per second square is of the order of 10 to the power minus 1 or 10 to the power minus 3, 10 to the power minus 4 or 10 to the power minus 2. You have to find out the answer for this. So, you know how to find out the answer for this. So one thing we know, see if I just think of, see you know this is actually a circular motion, the motion of this second hand of a clock or any hand of a clock is actually a rotational motion. Okay, so length of that is given, so that can be taken as radius. So let us take that as small n. So I know the time period. Okay, time period of a complete revolution, that is 60 seconds. So we have to find out acceleration. So can we use that somehow? Then see we need to see, we know this linear acceleration we have to find out here. See meter per second square means linear acceleration. So from here you can understand that okay, so do you know any relation between angular acceleration and linear acceleration? Okay, so linear acceleration in the sense, actually see here the acceleration means it will actually move in circular motion, so it requires a centripetal acceleration. So that centripetal acceleration we can find out is equal to omega square L. Okay, look now, omega is actually, see we know T is equal to 2 pi by omega. Okay, or I can write omega is equal to 2 pi by t. So 2 pi by t whole square this. So here actually you have to find out the average acceleration, means the centripetal acceleration. Okay. Actually this centripetal, like it has two components. One is along the radial direction, another one along the tangent direction. Okay. So and you have to actually find out this one, average acceleration. All right, so without much delay, let us do the calculation part. So this is 4 pi square by 60 second, and you look this is 0.1 meter. Okay, so I'll just do the calculation approximately. So 3.14, I'll just take nearly 3. Let me just do it here. So this is 4. This is, if I take this nearly 3, then it will be 9, and divided by this is 36 into 1000, right? So it is, yeah, 1000. So it is nearly 10 to the power minus 3 meter per second square. Okay, so I can say it is of the order of 10 to the power minus 3. Okay, this will be the answer. Since I have to calculate the order, so I did not mind to write this pi as 3.14. Okay, if I have to accurately write the value with decimals, then I have to go with the proper value, otherwise this is all right. Okay, so for knowing the order, it is all right. So this is how you have to find out the acceleration of the tip. Okay, acceleration of the tip, and that could be found out by calculating the acceleration, centripetal acceleration. Okay, all right, let us go to the next problem. So this problem is very important problem, and see, let us see the problem first. An insect is at the bottom of a hemispherical ditch of radius 1 meter. It crawls up the ditch but starts slipping after a height small h from the bottom. The coefficient of friction between the ground and the insect is given as 0.75. Now you have to find out what is the height. Height in meter. Excuse me. Okay, so look, first of all, let me draw a hemispherical ditch. That means I can just draw a hemisphere like this. Okay, just a minute. Like this. Okay, so if I just take this as center, so this is r radius, and this is also r, this is radius. And let us suppose when the insect crawl up to here, okay, it crawls up to certain height, okay, from the bottom, that is what it is said. So suppose this guy has come here, the insect crawled up to here, so this height is given as h from the bottom. This is small h. Now at this height, when it reaches, then it starts slipping down. This is the critical condition. Okay, just start slipping down. Okay, here, then what will be the height? Okay, this is very simple. If you can uh, if you can draw the free body diagram of the forces, see forces acting on this insect at this particular position. See, anyway, you know the mg mass. So let me draw this line. This is r, you know, and let us say this angle is theta. Okay, this angle is theta. This is theta. That means it is at an angle theta with respect to this vertical. So look this, if this has mass m, then the weight will be acting downward like this. It will be vertically downward, okay, like this. And this angle is again theta. So can I break this force into two components? One along this way, this is mg cos theta, and another along this way, okay, just tangential to the surface. Okay, this is mg sin theta, like this. And see, when it is slipping down, then friction will act tangentially upward direction like this, and see, when the component of weight is actually acting this way, so there will be, see, this is actually, see, if this is the wall of this ditch, so there is a force like this, so then there will be, so this mg cos theta is the force which is acting perpendicular to the wall of this ditch, so then that will give a normal force, so that is exactly equal to mg cos theta. Okay, this is n in the, it is acting opposite to this. Okay, so I hope you have understood this figure. Let me explain you once again. The problem says at particular height, small h, the insect starts slipping down. That means what? At that particular position, see, this mg sin theta is exactly equal to the frictional force. Okay, frictional force beyond that cannot hold it at this particular position. That is the condition. Okay, so I can write F is equal to mg sin theta. Okay, and then this is a frictional force. Okay, so that means, you know, this is mu into n, or this is mu into n. Maximum frictional force. Okay, and see, this n is equal to mg cos theta. We have already found out. So this mg cos theta and n will be equal, since there is no motion along this direction. Okay, so they will cancel each other. So if we just divide, or if I put the value of n over here, then simplify from this to relation, what I get mu is equal to tan of theta. Now mu is given, see, tan theta is equal to 0.75 mu. 0.75 means what? 0.75 means 3 by 4. Okay, so tan theta is 3 by 4. That can be found out. So what is the angle corresponding to this value? We'll be able to find out from little bit of geometrical concept. Look, if this is 4, this is 3, then it is 5. So it is a right angle. It is a right angle triangle, and see, this angle always is to be 37 degree, and this is to be 53 degree. Okay, from here you look, tan theta, that is perpendicular by base, that means 3 by 4 is equal to tan of 37. Okay, tan of 37 degree. So this means theta is 37 degree. Excuse me. So when I get this theta 37 degree, now look, I'll go to this point. See, I have this is R, okay, and this is theta, which is 37 degree. Now this figure, you just think this one, okay. So look, this part is actually R cos theta. So H will be R minus R cos theta. I have to find out H. That is what was the question. See, this figure only I have drawn here with a little bit simplifications. Okay. So H is equal to R cos theta minus of, sorry, R minus R cos theta. So this is R cos theta. Cos theta means cos 37 degree here. So cos 37 degree means what? Cos of 37 degree is, see from here, cos means base by hypotenuse. Okay, this is cos 37. So it is 4 by 5. It is 4 by 5. Okay, so this I can write here 1 minus of cos of theta. So theta is actually 37 degree. So I can write this. Okay, so this is actually becoming R by 5. That means what? 0.2 R. And R is given in the problem as 1 meter. So what is the height? Height is 0.2 meters. So this is the answer. Look here. So this is very simple. If you can understand that this is a critical situation where the mg sin theta and the frictional force will be equal. Beyond that, the frictional force will not be able to hold up here this insect. This will suddenly certainly come down. Okay, all right, so let us go to the next problem. This is another problem which is also very simple problem. So look, let us understand the problem first. 4-point masses, see, 4-point masses, each of mass m are fixed at the corners of a square of side L. So these are L. 4 masses are there. See, this one, this one, this one, and this one. The square is rotated with angular frequency omega about the axis passing through one of the corners of the square and parallel to its diagonal. See, axis which is passing through one of the corner, this is the axis, and this is parallel to the corner. Sorry, parallel to one of the diagonal. As shown in the figure, so figure is very clear. The angular momentum of the square about this axis. Angular momentum of the square about this axis. So what you can think of angular momentum here? So only mass is given and the distance square like length of the square side length like sides of the square is given, and see these options: ml square omega, 3 ml square omega, 2 ml square omega, 4 ml square omega. So what we can think here? So rotation is there, angular momentum you have to find out. We know, see, if somehow we can find out the moment of inertia of this all these four masses, okay, moment of inertia of this object itself. This is not a seat or something. There's individual particles. We can find out the distances so that we can find out the moment of inertia about this axis. Okay. So once you get the moment of inertia, then things are done. So L is equal to I omega. Omega is given. So you have to find out moment of inertia of this object or the configuration of the mass. Moment of inertia. So that is the problem now. Okay. So how to find out moment of inertia? See, I know for a point mass we know m L square. For a point mass is known, and if you know the distance between the point mass to the axis, then it is done. So look here, we have to find out the perpendicular distance. Okay, so if we draw this diagonal, so this distance from this mass, okay, so I get for mass this one. Suppose this is 1, this is mass 2, this is mass 3, this is mass 4. So moment of inertia is 0 for the mass 4, right? Because this is on the axis, so there will be no moment of inertia. So moment of inertia, suppose I1 for the mass 1. So m into the distance. This is actually the corner. Sorry, this is the length of the diagonal. Okay, length of a diagonal will be, for a square, it will be root 2 into L. So I get root 2 into L whole square. This is one. Moment of inertia of this mass and this mass we have to find out. So this distance, see, this is actually perpendicular distance, isn't it? This distance. And for this distance also, they are actually equal distance from this axis. Okay. So this distance is half of the diagonal. Okay. So I can write 2 into m. Half of the diagonal is L by root 2 whole square. Okay, so this is actually the total moment of inertia. So if I write, this is the total moment of inertia. So total moment of inertia about this axis we will be able to find out from here. This is square. So this is 2m L square plus 2 into m L square by 2. This 2 goes off. So you get 3m L square. So this is the moment of inertia, okay, of the whole masses, like all the masses except this 4, because it will have 0 moment of inertia. Okay. Now see, what is the angular momentum? L is equal to I omega. I is 3ml square and omega. So this is the answer. All right. So let us go to the next problem. Okay, this is also a very good problem. If you, so this is sometime memory based also. If you know the answer, you can directly write. So shown in the figure is a hollow ice cream cone. It open at top. It is open at top. You know, it is hollow actually. It is hollow cone. Okay. If its mass is capital M, radius at top is capital R, and height is capital H, then what is the moment of inertia about its axis is? So the people who have already marked up this, or you have remembered, like moment of inertia for various geometries, so you know this will be the answer. But how to solve this derivation? If somebody asks you to do the derivation of this moment of inertia, so then it is very simple. Look, let me consider a ring. Since it is cone, you can just think of a ring. Okay, so you think a ring like this, and if you keep on gathering ring of greater and greater radius, then you get a hollow cone. Okay, all right. So I can just consider a ring at some certain distance y, say at a y distance. I just consider a ring of thickness dy. Okay, thickness dy. Okay, all right. And suppose the elemental ring has radius smaller. So what I have done here, I have considered, see from the apex, okay, from this point, I have considered a thick ring which 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 has radius smaller, and it is considered at a distance y from this apex, and it has thickness dy. So moment of inertia I can write for this elemental moment of inertia will be di is equal to dm into, see about this axis, what is the, see for a ring, for a ring, what is the moment of inertia? M r square, right? M r square about its own axis. Okay, about its own axis. So suppose it has mass dm and r is the radius, so m r square. Okay, now what is this dm? You have to write down. So dm, that means mass of this elemental ring is given by the mass density into the area. Okay, area for a ring, you will get area, right? Thick ring, you will get area. So the area will be 2 pi 2 pi dy. Okay, actually sorry, 2 pi r dy. Okay, 2 pi r into dy, that will be the area of the thick thick ring. Okay, ring will have this much area. Okay, so what is this mass? See, mass density rho here, actually mass density means mass per unit area. So what is the area of this whole? The mass is capital M for the whole cone, and what is the area of this circumference, like it lateral area, that will be, for a cone it is pi r l, pi r and h is the height, length. Okay, now see dm I can write down like this. See, this rho I'll write m by pi r h into 2 pi small r dy. This, sorry, this r will be there, pi will be cancelled out, pi will be cancelled out. So pi m 2m by rh, these are all constant, and this r and dy, these are two variable quantity here. Now if I put it here, so I can simply write di is equal to dm, that means 2m by rh small r into dy into r square. That means you get 2m by rh r cube dy. Okay, now look this figure. I have two variable quantities, one is smaller, another one is y. So then I have to actually see, I have, if I want to do, see dy is there, that means I want to do integration of the variable which has y variation, but r variation we are not very much fond of keeping it here in the expression, smaller variation. So we'll actually try to get the small r in terms of the other variable y and h. Okay, y and capital R, etc. So see, I can apply the similar triangle. Okay, rule for the similar triangle is this: say small r by capital R is equal to small y by capital H. Okay. All right. So from here I can find out. See, y r capital R by H, small r is equal to. So look, then I can do the integration dy. See, integration will be y, right? It will go up to H on y. See, integration will be 2m, see 2m by 5, sorry, yes, RH will be there only. 2m by RH, then r cube dy, it was like this. Then I have to replace this r cube. Okay, so 2m by RH, let us keep this here, 0 to capital H. So 0 to capital H, r cube means y into r by h. This is whole cube into dy. Yes. Now everything is done. We have to just do the integration part. So we get 2m by rh, and here you get r cube, here h cube. Okay. And see here, this is y cube dy, and this will be 0 to h. So I can write here 2m r square by h to the power 4, and see from the integration I get 1 by 4 y to the power 4, and if you put the limit it is h to the power 4. So h to the power 4, h to the power 4 cancel out, and this is 2. So you get m r square by 2. So this is actually moment of inertia of this hollow cone about its own axis. See, it is just like m r square. So this is moment of inertia of the ring about its diameter. Okay, so that is what is the answer. Okay, so m r square by 2. I hope you have understood this derivations and you can apply it later. Now let us go to the next problem. This problem says a satellite is an elliptical orbit. Sorry, a satellite is in an elliptical orbit around P, a planet. Okay, elliptical orbit. Let us say this is the orbit. This is kind of an elliptical orbit. So when an astronomical object revolves around some planet or something about an elliptical orbit, so sometime, suppose this is the planet. Okay, this is the planet and satellite is here sometime. This satellite, this is planet. When it is sometime here, it is actually far away. Okay, suppose this is R2 away, R2 distance away, and when it is here, this satellite is here. See, this distance is actually lesser. Okay, this distance is lesser. That is R1 say. Now the question. Now read the question. When it is farthest from, see, it is observed that the velocity of the satellite, see, at each point there is certain velocity, right? So velocity of the satellite when it is farthest from the planet, that means this point is 6 times less. That means if the velocity, okay, less than when it is closest to the planet. Okay, it is close to the planet. I think I'll just put it in another way. I have to draw this on the major axis itself. So suppose this is the position of the planet. So this is the farthest distance. Just little correction here, because this distance R1 and R2 will just take this major axis itself, and this is R1 say. So when this satellite is here, it has velocity, suppose v1, and here it has velocity v2. According to the question, see, when it is at the farthest from the planet, so here, then its velocity is 6 times less than that when it is closest to the planet. So that means v2 is actually going to be equal to v1 by 6. This is what is given. Now the ratio of distances between the satellite and planet. See, these are the distances between the satellite and planet, R1 and R2, at closest and farthest. So R1 is at the closest and farthest is R2. So you have to find out the ratio of the distances between the satellite and planet at closest and the farthest. So the problem is this one. You have to find out what is this ratio. So this is actually very simple. Very simple. What you have to apply? Angular momentum conservation. Okay. Sorry. Conservation of angular momentum. So at this position, angular momentum, suppose L1, and here it is L2. So L1 is, this is M V1 R1. See, angular momentum will be always conserved. So at this position, it is M V2 R2. So this will be equal according to conservation law of momentum. So from here, actually, we'll be able to find out R1 by R2 is equal to V2 by V1. What is this V2? V2 is actually V1 by 6, and V1, let us take that as V1 itself. So you get 1 over 6. So what is the ratio? R1 is to R2 will be 1 is to 6. Okay, so 1 is to 6. So this is the answer. All right, we'll go to the next problem. let us see this problem. This is also very, very important and also interesting problem. So an object of mass m is suspended at the end of the massless wire. Let me draw the situation. This is massless straight wire. Let us suppose this is some, okay, this is some rigid, what to say, ceiling or something, from where the wire is hanging, say, and a mass m is just put on here. Okay, just place here some mass m. See, the wire had length, see, it is massless and it has some certain length L initially, and cross sectional area is given A. Now Young modulus of the wire is also suppose Y. If the mass is pulled down a little bit, just pull it and then leave, then what will happen? It will actually oscillate. Okay, it will oscillate. Since this wire is elastic, it will oscillate vertically like this. It will oscillate. So this frequency of this oscillation, vertical oscillation, you have to find out. So how to do this problem? You know, for oscillation, for SHM, we will just take everything as SHM, whatever oscillation it may be asked, we will just take as simple harmonic oscillation. Otherwise, you will not be able to find out frequency. So I'll be just considering this due to this mass. See, it has got little bit of stretch. See, let us say earlier it was L, now the length has increased by delta L. Okay, length has increased by delta L. So there will be strain in this wire. Okay, so what is the strain? Delta L by L. And see what we know, see the stress in this will be, so there will be a tension. Okay, so that tension is equal to mg, and we know the area of cross section is A. So can I find out Young modulus is equal to see stress by strain. Stress is force by area into strain. Strain is here delta L by L. This is strain. Okay, this is strain, and stress is this one, F by A. So F is actually mg. Okay, let us just do one thing here. Let me write F is equal to y into delta L by L into A, or YA divided by L into delta L. Look, this is the displacement. Okay, displacement of the wire. So you can see here force is directly proportional to displacement. So this is actually an indication of, so this is kind of a spring force, and you know I can write this by analogy. F is equal to kx. Okay, so I can write F is equal to kx. F is equal to kx. So here, see, F is equal to kx. So this delta L is the x here. Okay, so delta L is x, and this is actually force. So we know for a simple harmonic oscillator, the acceleration will be k by m x. Okay, so this k by m, so minus omega square x. Here I'm taking the modulus or magnitude, say, so I can actually get k by m here. See, this force will be actually, acceleration will be a, so m into a. So if you multiply here the m, then you get the acceleration, which is directly proportional to the displacement. Okay, so I can write here omega square is equal to k by m, which is here is ya by l ml. Okay, ya by ml. So this is the one. Okay, this is actually omega square. So I have to find out frequency, right? So let me find then omega. Omega is square root of YA by ML. What is frequency? 2 pi A this side. So I have to divide with 2 pi. So pi. So 1 over 2 pi square root of YA by ML. So this will be the frequency. I hope there is option like that. So YA by ML. So option B will be the correct answer for this question. So whenever there is a problem like this, that it is traced and then you have to find out the frequency, so you have to always look for this K by M, and before that we have to find out the force on this, which is directly proportional to the displacement. That has to be found out first. Okay, so now let us go to the next problem. I think yeah, so this will be the last problem for this session. So molecules of an ideal gas are known to have 3 translational degrees of freedom, okay, degrees of freedom, and 2 rotational degrees of freedom. The gas is maintained at constant temperature T. The total internal energy U of 1 mole, okay, of a mole, it is written, of a mole of this gas, and the value of Cp by Cv, that is gamma, for the gas. Okay, so you have to find out which one out of these 4 options is correct. See, first of all, degrees of freedom, actually there are 3 degrees of freedom, generally 3 degrees of freedom, 3 types of degrees of freedom. One is translation, translation, translational degrees of freedom, rotational degrees of freedom, okay, and another one was vibrational degrees of freedom. This is a vibrational degrees of freedom. So vibrational degrees of freedom also is there. Okay, but this vibrational degrees of freedom, these are active in the high temperature region, as good as 1000 degrees centigrade, etc. Okay, so no, sorry, 1000 Kelvin and all. So it is like even at 500 Kelvin also is going, it will be activated. So we are not considering vibrational degrees of freedom here. So total degrees of freedom actually will be, total degrees of freedom will be the sum of this translational degrees of freedom, rotational degrees of freedom, and vibrational. Anyway, it is not there in this case. So now it is given 3 is translational degrees of freedom and 2 are rotational. So I can get that the degrees of freedom is 5 for this. So once you get degrees of freedom, then how to find out internal energy? Actually, internal energy is found out. See, each degrees of freedom will take half kT energy, and see, if I know the mole, number of mole, then the degrees of freedom into half kT or half RT. So this will be actually, so this is mole, number of mole. And anyway, number of mole is 1, okay, so in this case 1 mole gas, and we know 5 is the degrees of freedom, so I get internal energy of this gas as 5 by 2 RT, 5 by 2 RT. And look, there are so many places, see at least B and C, there are 5 by 2 RT are there. Now the question is how to find out this gamma. So if you know the degrees of freedom, then finding gamma will not be very difficult. So if you know this formula, otherwise you have to find out Cp and Cv all the way. See, okay, Cv anyway, Cv will get du by dt. So that is du by dt, that is actually 5 by 2 r. So this is your degrees of, this is Cv, then Cp minus Cv is equal to r, then Cp is equal to 1 plus 5 by 2 r, then it is 7 by 2 r. Okay, now you have to take ratio of these two. Otherwise, the simple formula is say 1 plus 2 by f, 2 by degrees of freedom. 1 plus 2 by degrees of freedom. So 1 plus 2 by degrees of freedom, 2 is how much? Sorry, degrees of freedom is how many? 5. So you get 7 by 5. 755. So I have got degrees of freedom, sorry, gamma, that is the ratio of the specific heat at constant temperature and constant pressure and constant volume, is found to be 7 by 5. So you get C 5 by, so 7 by 5. This one is the answer. All right. So with this, I'll stop it here for today. In the next class, we'll continue with this POIQ discussions. Okay. So thank you for your patience. Bye for today.